So we made the conclusion what we are getting from the wing contribution. Now we will look into how the tail is contributing to longitudinal stability. So we have a figure over here. We can just analyze this figure and just get acquainted with the variable before we get into the mathematical details. So we have a horizontal tail over here, and it have some tail incident angle, which is denoted as IT, and it has some downwash angle. So what is downwash angle? So actually the wind which passes over the wing, that comes to the tail. So the tail doesn't see the actual velocity v infinity, rather it sees the vt. So the velocity also changed, and at the same time the angle that the tail will see of incoming flow, that will be different because of the downwash happening when the airflow leaves the wing and approaches the tail. So we are considering that change in angle as a downwash angle, denoting here as a epsilon, and then we have the effective angle of attack that actually the tail is going to see is alpha t. So this angle is coming from the wing, which is denoted over here, and then it reduces by the downwash angle, and then we have certain tail incidence angle. Tail incidence angle is also sometimes referred as tail setting angle. And in this we have the distance of tail from center of gravity. Horizontal distance is LT and vertical distance is ZCZT. So when we will resolve these forces, the lift and drag acting on the moment, and we can express the moment about tail in this form. As for the wing we had certain assumptions, in the same way we have certain assumptions for the tail over here, that all angles are small, and z, which is the vertical distance, is very small, and moment about aerodynamic center of tail is small, and drag is also very small than the lift. So when we will put this all assumptions in this particular equation, we can neglect these terms, and we will left with only this particular term, which is LT is the distance, horizontal distance between tail and center of gravity, and capital LT is the lift at tail. Since here a star is the alpha t, which is the effective angle of attack, which is denoted by the star over here. Since we consider that it is a small angle, so this is just going to become 1. We can express this lift at tail in terms of coefficients, where Q bar T is a dynamic pressure at tail, and when we will divide both sides with this particular term, we can express the moment at tail in terms of moment coefficients, and in the right hand side we will get something like this. We can further reduce this in terms of this, where our VH is horizontal tail volume ratio, while eta is the ratio of dynamic pressure at the tail and dynamic pressure in the free stream. Now looking at this, this is the same equation that is coming over here. Looking at this, we should ask a question, that is it possible to express the right hand side of this equation in something in this form, the y-intercept and slope, and multiplied with the angle of attack. If we can do that, we will know that how much the tail is contributing to moment at 0 angle of attack and how much it is contributing to the slope. And to do that, we have the lift coefficient at the tail over here, that we can express further in a straight line form, which is y-intercept, and this is y-intercept, and this is slope, which comes from this here a straight line equation. And since we've seen that the tail have certain different angle, and that can be expressed at this tail angle of attack, and we can express this downwash in this straight line equation, where this is the initial downwash angle and this is the slope for the downwash with respect to angle of attack. Generally the downwash angle comes from theoretical analysis such as Prandtl lifting line theory or some experimental. Generally for the practical purpose, people or researcher use it from the experiment. So once we have the expression for the tail lift coefficient, We can express that in this particular equation, and we will get the y-intercept and slope. So this is, we are seeing over here, is the moment contribution from the tail. So this first term is the contribution to the moment at zero angle of attack, which is over here, and this is second term is basically contributing to the slope. So now we have the main equation here, which is the we started with this criteria. We want to have this as a positive and this as a negative, because we want the slope to be negative, and this is essential for having the longitudinal stability. Now we see that in this first term the contribution is from the wing, this is contribution from the wing, and this is contribution from the tail. In the same way, in the slope we have the contribution from the wing and then the contribution from the tail. Now writing this further, we said that for at zero lift, at zero angle of attack, the lift is 0, so this term will be 0. So this is contribution basically from the wing, and this is contribution coming from the tail. And in the same way over here, this is from wing and this is from tail. As we've seen that the contribution from the wing alone to the longitudinal stability is in general destabilizing. Now to have the stability, we want this particular CMO, which is the moment at moment about center of gravity at zero angle of attack, to be positive. Now to have the positive, if we have this IT very large, and we consider the IT when we was deriving our equation, we consider the IT as this as a positive, and we end up with this equation. So if our IT is going to be very large, it is going to make this term, second term, as negative. So what if, rather than having, if this is our positive direction of assuming the IT, which is a tail incidence angle, if we have used this IT in this form considering the negative, so this negative over here and this negative will multiply with each other and it will make this term positive, right? So IT, to have the longitudinal stability, the tail setting angle or tail incidence angle should be negative in the downward direction, so that it will make the second term positive and the whole this term is going to be positive, and that is needed for the longitudinal stability. If we look at the slope contribution, we've seen that the first term, which is from the wing, is generally positive, but we want this whole term to be negative. Now to have this whole term to be negative, we have to make sure that the second term is large enough, and to have the second term large enough, the VH, which is the tail volume ratio, is a main contributor, and we want it to be larger and larger so that it will have the larger negative term and it will make whole the term negative, and it depend on our LT and ST. So LT is the horizontal distance between the tail and the center of gravity, so, and while the ST is the surface area of tail. So we have to make sure that these terms are large enough so that it will make the tail volume ratio large enough so this whole term will be negative, and that is needed for the static longitudinal stability. So here is our main outcomes from this discussion. We established the criteria to have the static longitudinal stability, that our moment at zero angle of attack about the center of gravity must be positive, and the moment slope with respect to angle of attack must be negative. We also seen the contribution of wing alone to longitudinal stability in general is unstable and destabilizing, but the combination of wing and tail, that is what make the airplane longitudinally stable. We also seen that there is a significant importance of this tail incidence angle and the tail volume ratio that contribute to longitudinal stability. With this, I will end this lecture, and thank you for all your time.